having me once again. It's great to be here. So before I guess I begin, I should start with a disclaimer, which is almost all of what I have to say is almost none of this is really, so to speak, new in a certain sense. What I will say will probably have the element of collecting various things together to form a part of one story, but it's not, strictly speaking, completely really new, or I mean, as you can imagine as we go along. All right, so that's enough of apology. Now, so first I should thank the collaborators, of course, excellent people, a week student in Saha Institute, and of course Rohan is conveniently placed to answer all your questions. And we have managed to put out one sort of summary of the things that basically it's a collection of observations, etc., that we make, and there will be a slightly elaborate version of this thing sometime soon, I hope. And well, I don't think we should stop there. There are more questions than answers that we are actually offering. So with that, let me begin. So a brief outline would be of this sort. So I will start with some motivation and some introduction, although probably it's completely standard by now, and I could probably skip it completely, but nevertheless, let's just have it. So here I will talk about one particular notion of chaos, which has become very popular recently, and then once the motivation part is sort of over, I will go on to discussing basically strings and this OTOCs, these out of time ordered correlators, specifically from the context of or from the perspective of this maximal chaos. What I say is maximal chaos on the worldsheet, but you will see that I neither have a very specific worldsheet description nor a very specific target space. It's a mixture of probably both, but nevertheless. So that would be the second point, and then the statement would be trying to extract some effective action or some effective description of this sort of physics in the form of a Schwarzian piece, which is very well known and very well studied.
So you have chaos on the worldsheet.
Well, it will probably become much more clear what I mean. So yes, this is, as I said, this is a very bad way of saying this, but I don't know any other way of saying it in a concise way. So let's go with it. It's, yeah, I mean, it's not quite the worldsheet really. Okay, so then yeah, I mean, then there will be some Schwarzian action. I mean, you could immediately guess where this could come from, but well, nevertheless, we'll have this. And the point would be also not just to have the Schwarzian action, but also to describe, or at least in principle, write down or lay out a method in which you could describe how this Schwarzian action or Schwarzian piece couples with all sorts of fluctuations with the strings and so on. So enough with the strings. I will, well, it's a very, very partial story, but I will have to move on from here to something on a D brane. Here I don't have any effective description except for one obvious case in terms of Schwarzian or anything, but hopefully it will become clear why I am trying to also do this, or I am trying to describe this. And then of course I will conclude with some outlook, possibly future work, and possibly this is the biggest part of the talk. Well, I mean, I will not make it the biggest part, but that deserves the biggest slot. Okay. All right, so very basic idea of chaos. This is something everybody knows very well. Chaos is all too familiar for us. So in terms of classical system, whenever we talk about classical dynamics, we talk about trajectories, and chaos is, roughly speaking, the following fact that if I have two very nearby initial conditions and have a dynamical system which is evolving in time, even though these two trajectories are very close in terms of the initial conditions, at sufficiently later time, they are not necessarily close, or their distance is not necessarily order 1. It can actually keep growing very, very large. So that's the idea of the initial perturbation, and I mean the result of the initial perturbation growing very fast as an exponential growth. So of course, the obvious way to characterize this is to take the trajectory and take an estimate basically this ratio del qt as you change del q of 0, which is nothing but a Poisson bracket, and if this grows with exponentially, this is what we call chaos. Essentially, it's a large separation.
When I studied dynamical systems as another, this was called sensitive dependence on initial conditions.
Yeah.
Chaos was much more complicated and much more sophisticated notion about what happens in the nonlinear regime.
Yes, yes, yeah.
Yes, I never had the benefit. Is that right? So if you had exponential dependence, that's not enough.
That's not enough for what people technically call chaos, is what is my understanding.
I see.
But
It's
it- but-
beyond small perturbation.
There's this attractor behavior, and strange attractors. I got them.
Okay,
But-
Lyapunov is not just is exponential dependence on initial condition.
It is.
It is.
Yeah,
In that more sophisticated.
In the more sophisticated thing, chaos doesn't refer to this linearized regime. It refers to the nonlinear behavior after this arrangement.
I see. But Lyapunov does.
Lyapunov refers to this.
Yeah. But
And
so,
just the chaos, I think, in value is.
Why do you call this linearized?
Linearized
It grows exponentially.
It grows exponentially, but this exponential growth comes from an eigenvalue behavior.
yeah.
So you've got some fixed point, you linearize around it, you get this exponential behavior. And then when you go to the nonlinear regime, this is not true anymore.
Maybe you're asking how does Q of t change under a small change?
Right, but the change is not necessarily small.
Yeah, but there's a prefactor, this whole thing will work as long as the whole thing is small.
And the criteria here is a small change.
Yeah, yeah, yeah.
Otherwise, you would not just be able to examine that. on the
Formulate
basis
this.
of one.
Yeah, yeah. So, but
there is chaos, then this guy, is a good description that it's not stable motion around the fixed point,
uh-huh.
and but first you have to have the breakdown of the integrity, the fact that it's not the phase space is not a torus,
Right.
all that. With that, this will become correct.
So you're saying the arrow is the other way. If I have chaos, this is guaranteed, but not the other way around.
Chaos is a bigger deal.
Chaos is a bigger deal.
So higher point correlators can be observed this more sophisticated.
You have to have some in the classical mechanics picture. Basically you have to have the some global picture of the phase space, in which it's not given by phase space is not a torus.
That's talking about breakdown of integrity. That's not the same as chaos.
It's not the same as chaos.
I'm sorry to
It's a bunch of loose definitions.
No, but however you define it, this is not chaos. For instance, this can end up in limit cycles,
Yeah.
which
That's
is not
right.
chaos.
That's right. That's right.
Yeah.
But it's okay if you use it for Lyapunov.
Yeah. So yes. So for this purpose, I will just I mean just Lyapunov exponent and nothing else.
Yeah,
This
yeah,
is just,
all of the string theory field calls this chaos. That's
yeah, yeah.
Very finely tuned condition.
No, I mean, let's say you start, there are many things, but let's say you start from some fixed point. Then you linearize around that, you get this exponential growth. Then you want to know where does it end up now. Okay, many things can happen. One of the standard things is it ends up in another fixed point. Another standard thing is it ends up in a limit cycle. Then another thing is that it ends up in what they call an attractor. And there's this thing called a strange attractor, which is closely related to chaos. Now, I'm exceeding my knowledge.
So then it's not even a statement about potential condition. It's about various the possibility of trajectories. What kind of trajectory?
There are two things. This is the thing. You start with a simple initial condition and it could lead to chaos. Then there's also the question of perturbing once you have it. It's a very complicated subject.
To paraphrase it, if I may, and I might be wrong in borrowing terminology incorrectly from the RG, this establishes that you have a relevant operator, but where you end up
Yeah.
independent.
That's-
Yeah, so this
that's-
is the same. What's the dimension of the relevant operator?
That is right. Yes.
Okay,
Yes.
sorry.
Yeah. Yeah. Yes. Right. So this is basically, I mean, this is the standard thing that people do these days. So yes, we will indeed talk about the Lyapunov exponent. So of course this is classical, and as you already know that the classical is hard enough, but I'm going to go to quantum, which is even worse in some sense. Actually, I did scratch my head quite a bit trying to understand quantum notion of chaos, and then I finally decided it's better to give up that and just accept it. So what I'm going to do is a standard story that long back various people have already studied in various contexts. So the basic idea is that we cannot talk about trajectories now, we have to talk about operators. So what you do is obvious. Well, you take first of all not the full quantum sort of version, but take some sort of a semi-classical picture in which you replace the Poisson bracket in terms of a commutator with some h bar etc. sprinkled in the right places. So the idea of course would be now if this were growing exponentially with some meaning of it, and that is what we call chaos, or we extracted the Lyapunov exponent from it. Something similar should hold for this commutator, and indeed a generic diagnostic function, you might say, of extracting the Lyapunov exponent can be written like this, where w of t and v of 0 are two arbitrary self-adjoint operators, and you calculate the commutator. I'm assuming here that the commutator does not vanish, otherwise it will not be meaningful. And you do not just calculate the commutator of this, you calculate the commutator raised to some power. So this is some integer, and the standard, there is another step which is the best, well, at least the best that I understand cases in which this can serve as a diagnostic function are cases when you calculate this expectation value with a thermal state, not for any arbitrary state. So as you can see, there are many questions that you can ask even at this stage. What happens if you relax thermal state, and etc., etc. I don't know the answers to. I'm not sure if these answers are available, but okay.
One question of that nature. If we worked with a particular state, would we be able to get away with just a single commutator rather than n equals 2?
You mean you want to say the exponential behavior of that?
For a particular state, would we see this exponential growth even in n equals 1? Is n equals 2 needed because phases average out in thermal equilibrium?
That is the standard argument that I also know, but of course I don't know whether you can actually design a state in which by calculating the 2-point function you do see an exponential behavior. I don't think it's ruled out. I mean, I don't know any general principle why that would not be the case. But
states you can have 1-point functions for suitable operators, right? I mean,
yeah.
the energy is the obvious one, but that may be too simple. I'm just asking, in that case, could you get away with n equals 1 even for?
It just seems too simple, because with the n equals 1, it's a 2-point function, so there's no out of time order. It's too simple an object, it never disappears.
I mean, the 2-point functions will always tend to decay. Thermal systems has this problem that if you inject energy, it will start thermalizing, and then you never see exponential growth. That's the way at least I understand this statement. But of course, you could come up with some state which is special enough, that still gives you some exponential behavior.
The way you formulate it is a sort of 4-point function, and then you want to take these cross ratios in the context of CFT. So that seems like some sort of a Ray type.
Yeah, yeah.
Which you go, because you're taking the commutator, you want to at least compute one distributivity.
Right.
Which would involve taking it around and you want to probe its behavior large times, meaning you want to collide it with one of the boundary, one of the operators that are creating the state.
Yeah.
This is just some.
That is rough. Yeah.
And so with this expectation, do you think it's possibly going to grow exponentially? It's just that this Ray limit. Yeah. That's correct. But yeah. Okay, sounds good.
I can have out of time order even for odd number of operators like 5.
Yeah, yeah.
Right. Anything more than
More than 2 is fine.
2, yeah. But a 2, because you insert one operator here, you think you might be inserting it far away on the contour. But you can always move the contour, right? So it's not far away. Yeah. Okay.
No, but this might be an interesting. I mean, if you can cook up examples where you can see with a 2-point function this exponential behavior, that might be, at least I don't know. I mean, sufficiently generic, or actually even one example of that. Okay, so that's yeah. So that's certainly one obvious question that you can ask. Yeah, yeah. Yeah. Right. Right. Yeah. I mean, you have to cook up some state which does not look like a thermal state. I mean, I don't exactly know what that might be, but
So just to, since
yeah.
if I can just ask you a
Yeah,
detailed
yeah.
question, is there a connection between classical chaos and this quantum notion which one could go towards by using coherent states in an appropriate system? That is, if classical trajectories are diverging, and you can see that through lower endpoint functions than 4-point, could you take a classically chaotic system and
You're saying do a coherent superposition.
yeah, and then build it like I don't know, x to the 4 potential has some variant of chaos, right? So you take a coherent state and
I see.
I don't know.
X to the 4 potential with the 2 or more. 2 or more. Awesome.
Right. Right. Okay.
Right.
Take some coherent state. And, okay. Anyway, go ahead.
Yeah, I mean that I don't know if I don't know if anybody actually has tried that. But okay, so as you can already see that this well, okay, you can take n to be any integer which is bigger than 2, and you should get exponential growth with appropriate factors in front of the Lyapunov exponent and so on. So if you expand this, it's easy to check that basically what you have are essentially two kinds of 4-point functions. One is this standard time ordered, although I have ordered in the probably the reverse order, but okay. And then there is this piece which is out of time ordered. So and the understanding is of course also that this time ordered correlator is not going to show you any exponential growth. So the full object, the full contribution to the exponential growth is coming from an operator like this. So if you can calculate out, so basically at the end of the day, after all of this, so the whole point is reduces to calculating some bunch of out of time ordered correlators. And the simplest one is of course the 4-point function. And it's not easy to do these calculations in field theory, even in weakly coupled actually. So, okay. So that's the beginning of the quantum notion, and there is another perspective which I'll very briefly.
Has it been computed in perturbation theory, in any theory?
I think there was so yeah. This is what I was trying to look at. I think there was some calculation with FIFO theory, weakly coupled, but then what they have to do is somehow do a perturbation and also resum it. So there, I don't exactly remember whether you do see the chaos or not, but you can calculate the OTOC in that form.
Perturbation theory, I thought you just use the suitable propagators and you could do it. But you
On
have
a-
to resum? I mean, why can't you just do whatever? Use appropriate propagators, etc.
Oh, I'm sorry. So the resummation I think was more in the spirit of trying to get the exponential behavior. So if you don't do a resummation,
Okay, but just to compute it in perturbation.
to compute you can, yeah,
You should be able to, right?
yeah.
Euclidean theory and there will be yikes now.
Yeah, and then okay, but suitable.
Yeah. The problem with that is you're interested in very long time.
Yeah,
And Euclidean theory you can compute at discrete domain. So it's a bit, you'd have to, with some twist. You can't just do it in small omega Euclidean theory. That's the same kind of problem with computing viscosity. Typically that also involves a resummation to see
yeah.
the effect.
But just computing it with a suitable propagator, I'm sure is possible.
Yeah, I'm sure.
We're not sure anything interesting.
Yeah, no, but interestingly, I mean, to do it well enough to get the exponent.
Yes,
And
yes, yes.
that
Yeah, yeah.
exponent probably has a does it have non-trivial lambda? But
Probably first order lambda, because it has to collide.
Yeah.
So, but you'll have to sum up all those things that take you from power law to exponent. I think that would be the summation.
Yeah, I think it's exactly like this viscosity. This 1 over log lambda kind of thing appears in perturbation, which is very hard to get. But I have not, honestly, I have not quite understood I have not even attempted to understand.
The people who the first calculation of viscosity was by Yaffe and collaborators in the 1990s, and that was by very substantial work, summing infinite classes. So this would be, I think, so.
This would be something similar, yes.
On the other hand, if you already know, like in SOIK, that there's a soft sector and the effective action has a Schwarzian, the perturbative you get it at just the perturbative order, e to the power. There's no summation. Is it in some sense that the summation has already happened at the...
You're saying the Schwarzian itself controls, the solution to the Schwarzian equation is this exponential.
Yeah.
That's what you're saying.
Yeah.
Yeah, that's somehow different.
Yeah, that's good.
Yeah.
I mean, the Schwarzian itself does not quite have a perturbative sense in it, right? It's itself somehow non-perturbative. Yeah. So somehow, if you can repackage your things in terms of that, then you can. Okay. So it's a hard quantity to calculate. That's in general, of course. Well, okay. So let me just very briefly tell you what I understand of this picture. So this 4-point function or 4-point correlator here, it has a natural interpretation in terms of an amplitude of the following kind. So this diagram is, I have always been confused with this. So let me see if I can explain it. So what you do is, although I have not leveled, I should have done that. So let's say this horizontal line is some states. This is at t equal to 0. This is at some other not temperature, some other time. But this state is a thermal state to begin with. So what you do to that state is you insert some amount of energy. What's going to happen is it will thermalize and it will go to a thermal state, of course. But what also happens is that this final state does know something about this initial energy or perturbation that you put in the system. So this information is not completely lost. And
I'm sorry.
yeah.
Just maybe it's pedantic, but it's a thermal state.
Yes.
And you're calling it some ket.
Oh, sorry. That's
You have some TFT kind of thing in mind, or?
yeah, you can think of it like that. Yes. Yeah. So I mean, anyways, this ket is just a notation for me. I don't mean this is one. Yeah. But if you want, yes, this indeed does have a thermophile double picture. Very, very intuitive.
I mean, I'm saying that it's not a pure state.
It's not. No. You know, by this I don't mean it's a pure state. Okay. So right. So the idea is that if you take this final state and somehow could trace back, you could discover your initial configuration here. But now imagine the process that before you're trying to trace back, you hit the system with another excitation, which I call W of t, and now you take it back. The problem is, this being a thermal state, this excitation will also dissipate and it will again thermalize. So what you're going to discover is this, not this. So this is a particular state which you can call W of t V of 0 acting on beta. Take back in time, yes. So if it is thermal, you are probably not going to get this picture in general. So now the idea is to imagine exactly a reverse process. So suppose I call this state as an in state, which is specifically this particular object. You could have done this whole arrangement in the reverse order, and you could have ended up with something called an out state, where these two operators are switched. Of course, I'm assuming they don't commute. Then there is an equivalent sort of diagnostic of chaos, which is nothing but the amplitude of these two in states and out states. So that's the upshot of this whole thing. So evidently, what's happening is I'm just replacing the 4-point out of time ordered correlator in terms of an amplitude. That's all.
You don't have to be so tentative about it. There's a 4-point function. You think of it as an
Yeah.
in and out. That's all.
Yes. Yeah.
Okay, so
That's all.
in the black hole context, it's very evidently that.
Right. Right. Okay. Good. So let me just so this is something I just want to.
And what happened with, I didn't understand the ordering.
Mm-hmm.
If we had initially VW,
Yeah.
then you did a dagger that became WV.
Right.
That looks like in time order. Sorry, could you go back much? Right?
Yeah.
What was this? You're taking an inner product of a state with itself?
No.
No. But the
Maybe.
out was the dagger of in?
No.
Ultimately, the 4-point function he wants to compute, if
Yeah.
I'm right, is V of 0, W of t, V of 0, W of t.
Right. Right.
So now,
No, sorry. Maybe I have written this in.
the first W of t, V of 0 is in, and the other two after that.
Other two is just out.
So could you
Yeah,
write
yeah, yeah.
that down and write down which two states?
So let's see. So V0.
Oh, okay, all right. I was doing it the other way around.
I mean, it's the same thing. So this is my
Oh, your in is on that side.
in. So I have things switched over or something like that.
WTV of 0.
Out is this.
Out is that, but now if you make it a cake, it's WTV of 0.
It's WTV of 0. Yes.
So you're not taking an inner product of a state with itself. You're taking an inner product of a state with another state.
Right. Right.
Okay.
Right.
And was this transparency supposed to give you some physical motivation to understand why this would calculate for us? I didn't understand the physics.
No, I think. Let me see. Yes. It. All right. So what's supposed to happen is what you expect is that these way, I mean these two states, when you take a sandwich of that, at sufficiently late times, these are distinguishable states. So you should get a very small overlap. So it should approach 0. But that will not necessarily happen for all time. So that is sort of the understanding.
What is your implicit chaos bound loop? So you bound this quantity by the inner product probably, and then you say that will be in time order and that is decaying.
Yeah, it could be something like that.
You'll bound it by a constant, and then this thing will actually grow, right, until it reaches that constant. So how would you see that? Okay, I didn't understand what we can do.
Okay. So let me go to this particular picture. So basically, what's going to happen, or what's supposed to happen, is the following: that this C.
So sorry, really
Yeah,
sorry,
yeah.
you should go on and maybe this, but at least in the black hole context, what the advantage of thinking about it like this does is, it allows you to view the 4-point function as a scattering.
Yes. Yes.
And thinking about like what? Could you say it again?
As an inner product, that is, you think of it as the overlap between an in state and an out state.
Now, in-state and out-state in the two-sided system.
Right.
Or in the one-sided, but because you could even in the one-sided system have a scattering process where one shock wave starts close to the horizon and the other comes in from infinity, and after scattering, one goes off towards the boundary and the other one is inside, but you draw a space.
Okay, so it's an inner product between two different states.
Yes.
Yes.
And why should that show chaos? What is the intuition that that should show exponential growth?
No, that comes from the original transparency, but this is an efficient way to
Calculate.
Yeah.
I mean, at least in the black hole context, that's what.
Yeah. So it's just a way of rewriting the 4-point function so that we can
So the
calculate.
way of rewriting is
everything.
chaos.
Yeah.
Okay. But I thought
That's
that
right.
this way should give you some intuition for what was going on.
I'm not sure.
Again, in the black hole context, you get a huge relative boost, and so
Yeah.
the scattering is enhanced by that huge relative energy, and so it's immediately obvious that it's a scattering with a huge energy.
And should one think of this as a two-point function in a state? Or it's better to think of it in a product? Should one separate it into in the black hole context, the guy that makes the shock and the guy that does the probe? Is it useful to separate those two?
You could, although you could also just say it's two probes scattering,
Yeah.
and then in gravity the scattering is energy over g Newton.
Yeah.
It's a proper energy. Right?
Proper.
Right.
That's why it gets
Yeah.
revolution.
Yeah. I'll ask you at lunch. I want to understand this better.
Sandeep, is there some one-sided just equivalent
this. But I can come with
Yeah. So the one-sided kind is kind of built on this this sort of picture, right? You take you insert operators and you take a time reverse back configuration, and so on. Okay. So on this, so let me just very briefly say what this is supposed to be. One thing is, of course, we have introduced two functions. One is the c, which is the commutator square in this case. Let's forget about any other n. And then this amplitude. So what's supposed to happen is, this is a time axis. It's of course a cartoon. Is that so whenever you inject some energy beyond the, so what will happen is that the energy will sort of get thermalized beyond the dissipation time, but then this correlator will start growing, and this is basically a regime which is essential to see this exponential behavior. And for generic systems like this, it happens only if you have a scale separation between the dissipation time and what is called the scrambling time. Essentially, basically, this is basically the time where this particular function approaches, say, order 1 or something like that. And in this amplitude case, these two are related. If you wish, the sum of the two is essentially just 1. What happens is it starts from an order 1 quantity and then starts decreasing. So basically, this estimate, whenever it starts decreasing, gives you the dissipation time, and when it approaches close to 0, gives you the scrambling time. Sorry?
F of t is the
Just the amplitude.
Time ordered.
Out of time ordered.
F of
F of
t.
t.
C of t.
C of t has both time ordered as well as out of time ordered. So it's like, if you like, 1 plus out of time ordered or 1 minus out of time ordered.
With this one type of correlator, we should die already at TD, right?
Yeah, that's no.
So maybe can you say what f of t is exactly?
So f of t is just this. Now, what is C of t?
Oh, the commutator was the thing.
Yeah, C of t has all of this: V0, V0, WT, WT, plus say f of t. I'm being completely sketchy. So what if I normalize? If I divide by this on both sides, I will essentially, so this will approach 1 plus something times exponential lambda t. So the exponential growth you can see both in C and T and in f of t, but in just a complementary way. So they sum to be 1 if you wish. That's all. It's just a rewriting. But the whole physics point is in this. So you really need this separation, otherwise this exponential is not visible. So that's very, very essential. So I need a semi-classical theory or a system which has a semi-classical limit. Okay. So a few of, well, if you want to be doing holography, so there are a few favorites as semi-classical systems, and I just list them for no good reason in no particular order. This ON sort of vector theories, which give you higher spin theory and so on, and then SYK type model, which gives something probably far more complicated than either of these two, but nevertheless. And of course, finally, there is SUN gauge theories, which has large anomalous dimensions and just simply Einstein gravity. And in all these cases, the semi-classicalness is basically just given by a small parameter, which is 1 by number of degrees of freedom. So all of these systems, they have a well-defined semi-classical limit. That's all this is. And for all of this, you can actually set up this problem. Okay. So let me now describe what you do if you want to extract the Lyapunov exponent from event horizons. So this is again, this is not a pure state, but this is the thermophile double. This is what the Schenker-Stanford picture is. Then it is a pure state, yes. And then what you do to sort of visualize or recast your 4-point function calculation in terms of an amplitude calculation is imagine that there are 4, or there are rather 2 in states or 2 pulses in your in state and 2 pulses in your out state. and you are just taking the amplitude and evaluating the expectation value here. So yeah, so this object is something like this with some T1, T2, T3, T4 instead of 0 and T, but you can place them. And as you can see that this particular picture is obviously natural when you have the two-sided story. But I mean, as you were saying, there is a way to relate this two-sided story to a one-sided story simply by doing the following, that if you have an energy injection here, I don't have the story, but okay. If you have an energy injection here and you want to create a state which has two energy injection, one here and one here, what you do is take this state, time, go back in time, and then insert another excitation here. So that gives you two excitations in terms of essentially time slices which are purely defined on the right, and so on. So that basically has similarity with the picture in the initial slides.
So,
and then
Arnab, let me ask
yeah,
something.
yeah.
I should know the answer to, but anyway, there is this standard picture from Maldacena in 2001, which says that if you put insertions on the two-sided black hole, that relates to a Schwinger-Keldysh type contour.
Yes.
Right? It relates to insertions and a Schwinger-Keldysh. So
Right.
if I put any number of insertions on the left and any number of insertions on the right,
Right.
that is just a contour that goes back and comes forward, and that's not
Yes.
an OTOC.
That's not an OTOC.
Okay? So what here are you doing different that makes it an OTOC? I mean, it's not just you're not just turning on non-normalizable boundary conditions on the two sides, right? You're not doing that. So what?
He is turning on.
Yeah.
That's the way.
That's-
That's the way to generate the state.
Yes.
But I thought there was the standard picture. Is it just a wrong picture? That Maldacena had this picture which said that if you take this contour halfway down, this contour halfway down, insertions here calculate insertions on the right, insertions there, and insertions on the left. And that, since the contour has only two parts, is not an OTOC. You need four.
You need 4. Yes.
So my question is, in what you're calculating in gravity, why are you calculating what you claim to be calculating in field?
No, but here I thought.
Actually, interesting.
No, hold on a second. So but in this particular picture, you agree that this is a purely I can place T1, T2, T3, T4 in any order that I want.
What you're doing in gravity, I'd like to know exactly what you're doing in gravity. Then I would try to understand.
So in gravity, what we are doing is if you have a thermophile double like this, then you construct. So let's just take this to be a same time. If you wish, it's not 0, but okay, T1 and this is T2. So then this is VW or WV.
But it's not the same as turning on. No, this is something different. This is some state business.
Yes.
But can you manufacture? Is this the same as doing a calculation where you turn on sources on the two sides, or is it different?
Is this the calculation? I mean,
It's different from that, and I don't have a question. But I want to say how it's different.
well, I mean, these energies are coming from somewhere, so it's turning on something.
Would
Right.
you get the same exponential growth only by turning on, if in a correlator where you turn on two sources here and two sources here?
What I
No.
just allow
Yeah,
me to say
yeah,
one
yeah,
small
yeah.
thing, which is you can literally do the field theory calculation
Yes.
on the gravity
Right.
side by turning on sources only on one side and having a suitable state.
Ah.
You know.
True.
And then that's how I understand it. That the thermophile double just gives you the temperature. And
Yeah.
you're doing everything on one side, just as here you're turning on all the operations.
And that is manifestly an OTOC.
And that's manifestly a note.
Because you've got B on one side and B on the other, and you can't put that together.
Yeah, that's manifestly a note.
So, but this you presumably cannot get by just turning on sources.
Yeah. So there's, for example, the one which he chose, the green bump, which he took back in time.
Yeah, this
and
one.
Started over there. You would not be taking in the bulk. You would not be taking the normal metric. You would have to take it with that pulse which is coming from the right, excited.
And you cannot create that green bump by turning on a source, can you?
It's a non-normalizable. Non-normalizable.
Source is always non-normalizable.
You can, I think. I think you can.
It is.
Yeah. So my question is, can you turn on two sources on the left, one for the blue and one for the green, and two sources on the right, one for the blue and one for the green, and get this? I believe that would be a contradiction if you could do it. Because then you would be saying that you have in a non-OTOC this explanation.
Yeah. So,
So I believe the answer must be no.
Yeah.
But I wanted to see it more, in more detail how.
I see.
On the left, indentings run opposite.
Doesn't matter. It doesn't matter. You see, it's just two contours. One, you need four contours to see that. Four excursions.
Right.
One turning back at the bottom. That is,
Yeah.
I guess. Yeah, you need this part.
Okay.
Yeah.
Really sorry, how do you see so fast you need 4? You say you go from V of 0 to W of t, that is along, in your thing, that's a horizontal control. And then you switch back in time. Is that what you meant?
Yeah.
When you switch
Yeah.
back like that?
Yeah, you have to have the two things at large time separated by something at small time.
Hmm.
So you have to go, come
Mhm.
back, then insert that other thing, and then go and come back.
Hmm.
So to be separated,
You need 4 switch back. Okay.
we know
okay,
we need
okay.
4. So you want to see how that contour manifests in the.
I would like to see basically, firstly, how this is different from the thing that is manifestly not calculating this OTOC, and to get a very clear understanding of why this is calculating what you want to calculate.
Shiraz, would the source turn on in a shockwave?
That sounds reasonable because what Sandeep said. I mean, if you're in a state, if you're calculating expectation value in a state, then the thing that creates the state is on the extreme right for the ket and the extreme left for the bra, and then it's out of time.
Yeah.
Yeah.
Let's say the two V's are at small time
Right.
and the two W's are at large time, then it is out of time. That sounds reasonable. So if what you're doing is calculating expectation value in a state, that sounds reasonable. And then I would have to think a little bit about whether what you're doing in gravity is calculating expectation value in a state. But it sounds reasonable if you're doing it in a background.
Let me just say, this is why mapping it to an S matrix element helps, because you know, which was this part. If you map it to an S matrix and then you identify the in state and the out state, then you can think of it as the evolution. I mean, that is the calculation that I understand. And in that, some of the things can be created by sources.
Yeah.
The others are just initial conditions, right? Again.
Right. Right.
In
Right.
Hartman's picture, this is this thing. You have two states, and in the middle you put operators.
Exactly, and that sounds reasonable. Yeah, maybe the idea is that you can't create all of the state you need by sources just on the boundary. Some has to come from inside the block.
From inside. That's what
Yes.
happens in the scattering. That's what happens in the scattering.
Okay.
But it comes from inside. Sorry,
Yeah, yeah.
So please excuse me.
Sure.
I mean, it comes from inside the horizon, but had the other thing not been there, it would have hit the boundary somewhere.
Right.
That identifies what W of t it is, but the state is at the initial time. You know, that's the way you map it to.
But that makes it clear it cannot be created by creating a
Yeah,
source.
on that side.
Yeah.
Inside.
That's why I'm not sure how to map it here.
Yeah, and you shouldn't be able to.
Okay. Right. Yes. So in terms of the scattering, there are a couple of things that you can do, which is essentially simplifying this calculus, or to be able to do the calculation, which is the standard technique of elastic iconal scattering. What happens is, so basically you imagine that these are very highly energetic objects or pulses. So basically they go almost grazing the horizons, and what happens in an elastic collision is that the out state and the in states, they can at best vary up to a phase, which is essentially just a function of the Mandelstam variable S being P1 plus P2 square. And so this phase is the object that you want to calculate in the scattering process, and basically, so at the end of the day, this OTOC, which is as you said, it's a expectation value of the operator in a particular state, is equivalent to calculating an integral like this, where I am completely schematic. There are factors of momentum. There are objects which you can call wave functions, or these are basically what you get from the bulk to boundary propagators. And then there is this exponential I delta, which is essentially a function of S. And this is the calculation that you have to do. However, the problem is, well, I mean, one of the problem is that there are very few cases where you can actually do this calculation explicitly, because the psi is usually very complicated and you don't know what the bulk to boundary propagators look like in ADS. One example is obviously 3 dimensions, where you can do everything analytically, or at least most of the things analytically, and that gives you this this Lyapunov exponent is 2 pi t, which is essentially saturating the chaos bound.
Psi is what? Is the state.
Psi is the state, yes. It's a collection of, I mean, I'm just writing one function.
Special kind of bulk boundary propagator? Sorry, why is it so difficult?
No. So I mean, there's a black hole, right? So you have to be able to solve the equations of motion to find the. I mean, it's not empty space. The reason you can do it in BTZ because BTZ is diffeomorphic to.
So even though
Okay.
you can't do it in general, that is exponential dependence you can easily argue, right?
Yes, I would think so. Yeah. Yeah, you can argue based on the fact that there is this the amount of boost basically, but not from the form of a bulk to boundary propagator.
None of that ultimately matters, right? I mean, there is some bulk.
None of that matters. That is true.
What goes into delta of S in the end.
Yeah,
is
yeah.
just the-
It's just the exponential, this Rindler time business, precisely. So okay, so that's right. Now okay. So now you can ask a very simple.
Phase
Yeah,
shifts are related to time delays, right?
they are related to time delays. Yes.
So can I think of this as there's this shock wave, and as this probe goes through it, there's some time advance or delay,
Yeah.
and this is telling you how that time advance or delay varies as a function of time.
Mm-hmm.
There's also a sign, but you're not interested.
Yeah.
Whether there's
Yeah.
an advance or a delay, not interested.
Not particularly. No.
Well, it will be a delay.
Because it's gravity. Yeah.
Yes. Okay. So so there's a simple question that you can ask. Is the answer is almost obvious, but okay. The question is what gives you this maximal chaos? And you can do the first thing you can do is an example survey. Of course, there are black holes in gravity, which will give you this because of the Rindler time. We know the SYK.
Could you go back one transparency?
Yes, sure.
You have this delta of S,
Yeah.
and then you translated that into how does the delta of S translate into this exponential growth?
No, the delta of S doesn't quite turn into the exponential growth. So what you really need is, I think, this delta. As long as this delta is some growing linearly with momentum, and as long as this bulk to boundary propagator has a piece which is like this Rindler time, this exponential 2 pi over beta, then you are going to get this.
Actually, schematically, how so we know in gravity this is like S square by T, right? Delta
This is a square by t, yes. I mean p u p v. So or
in the T channel exchange, the dominant one.
a square by t or just s.
S in G Newton.
Yeah, just s, right?
Well, that's the 4-point exchange, the 4-point interaction. But there's also a propagator exchange in the T channel, which is S square by T. That's not the
So
dominant.
amplitude was a square by T.
Yes.
This is like two scalars, suppose two
Yeah.
scalars.
Oh, the time delay. Go on, sir.
Two scalars interacting by exchanging the graph.
Yes.
So there's a 1 by T because of the graviton exchange, because the propagator.
There are factors of momenta at the interaction vertices because the scalar couples derivatively.
Yes.
And there's the p square in the
Yeah.
denominator. But the net result is that it grows.
It grows with s.
It grows with the S in a way that has a T denominator.
No, I don't think so. Just G Newton. Dimensionally, there's a power of kappa at each of the two.
Yeah.
This is why gravity gets strongly coupled. This is that same calculation that says gravity gets strongly coupled at high energies, right? So
But what's the propagator
Extends this.
contributes inverse power of omega.
yeah, but that is just weights against the powers of momentum.
If you count net momentum, but one is an S and the other is a T. So
No, the net momentum is p square at each of the vertex.
But the diagram is not non-analytic. I mean, there's a pole, so it can't be completely.
No,
The
no,
wall
I'm,
scaling is the T square.
The usual thing is use G Newton times S.
Yes.
As a phase. Isn't that right?
yeah, that's what I also remember. But does it have anything to do with the iconal approximation? I mean, you're putting things in, you're putting the external legs on shell.
This answer you will be in iconal approximation, you sum the class of diagrams. It's like
Yes,
who gets
this
exponent.
this ladder.
Okay, first term there is just one graviton.
Yeah,
That's
the delta
right.
S is single. Then you expect.
Yeah.
Yes,
So that I thought was one graviton external.
that is what I also thought. Yeah.
With one power of G Newton,
Correct.
and the remaining things just were a function of S in this.
Yeah.
And that invariant energy was growing exponentially with
Right.
the boost, so the whole effect went exponentially.
Yeah, so the S
Right.
will grow exponentially, but I believe that the T-channel exchange scales like S square by T. That's the one which grows highest with S, because there's a T denominator, it goes there's a higher power in S. So that's the dominant one that large S means.
That's the amplitude. I
That's-
think the delta of S has a 1 power of S plus
One power of S. So let's say it's S by T.
S by T.
Now how does that convert it turn into?
It's not S by T.
Oh, it's not.
But yeah,
I don't think
that's
it's
why
S by T. We'll have to do it, but I'm pretty sure
it's G Newton times
it's
S.
G Newton's times S. Even in the Kamano whatever paper, the causality paper of Mandasena, it's G Newton times S.
Yeah, that's what I also thought.
It's not S by T, it's G Newton times S.
Sorry, what saying is?
Delta is some integral over the amplitude.
Ah.
That's how the T goes.
So the T goes away because
Oh, I
you
see,
so
I see,
particular
I see, I see.
position.
Okay.
Yeah.
I see.
And
Okay.
What is this?
He said you trade T for the impact time.
Ah.
Okay.
Okay.
You go to impact parameter space, S and impact parameter.
Oh, I see.
That's like a Fourier transform.
I see.
Oh, I see. But now I don't remember the but that's true.
Then it would go as S square.
But the definition of delta also has a 1 by S sitting.
That's fine. There's some.
I see.
Okay, if you
I
go to
see.
impact parameter space, I agree. There will be just
Okay, but then that's basically your point. So I'm sorry, then I don't remember the impact. But you're right.
No, the impact parameter does appear, right? I mean, there is a. I mean, if you write down this 4-point function, there's an integral over the impact parameter
So I
space
think
also.
that's what you're doing by the wave function parameter.
Yes.
Okay, I'm sorry. Yeah, there is that. Okay.
Okay, but just roughly, how does this go into exponential in time? Just very
So exponential in time, that purely comes from this piece. So what happens roughly is
So the form of the scattering amplitude doesn't matter, you're saying? How it grows with S doesn't
no, it matters. It matters. I think there are two things that matter. One is that this delta of S has to be momentum. By momentum, I mean the null momentum, of course, U or V. And then the other thing is that this psi has somewhere it has this exponential t, which is guaranteed if you have a Rindler structure. So this will be picked up, and what happens is when you do this integral, well, mechanically what happens is when you do this integral, you can do a variable change just to be able to do the p integral, and then this exponential, because of this variable change involving the psi of p and p, that exponential, I mean, so this exponential will come in front of the integral. So p by e to the power. So what you do is you do exactly it's some p tilde, which is p by, this is very schematic, e to the power t. Of course, there are all sorts of factors here and there, and when you do this, you get this e to the e to the t coming out of the integral.
If I'm understanding right, what you're saying is that whatever the S will give you a measure of the time you trade it for the center of mass S,
Yes.
and that will grow exponentially with t.
That will, yes. You mean this variable change and so on. Yes. Precisely.
Is it that whatever appears in the phase shift as a coefficient of S in the exponent will be the diagonal exponent?
No.
Now I'm wondering
Yeah.
corresponds to one factor of S, right? So
Yes.
what happens is this S square, I would have thought the typical impact parameter is RADS or something, I don't know. That doesn't grow with the boost. you know.
No.
So finally, what happens? The one S square S goes away. Is
Yeah,
the function overlapped?
It's probably in the translation between the phase shift and the time delay. Because
Phase shift and time
phase
delay.
is e to the power I e. You want to, when you know phase shift, then you want to translate that into a time delay. You have to do that with carefully.
Factor of momentum is sitting there.
I'm not getting the full S, I'm getting a square root S. But you know what I mean? The phase shift tells you how much longer you would have had to wait with free propagation. Free propagation is IET.
Mm-hmm.
So the phase shift is related to time delay by, phase shift is equal to square root S times time. Square root S times time delay is equal to phase shift. Where the extra square root S will take from here. But that's not
I
translation.
see. I see.
I mean, another way of saying it is phase shift is dimensionless. Whereas time delay has dimension.
Yeah. So no, that's what makes
So there is a factor of S.
G Newton, of course, has to stay G Newton.
Yeah.
And then finally, all the B and everything is just
Yeah.
one S stays around. And I must say, I don't remember. Sorry.
Yeah, I also don't
must have
remember.
remembered thinking that's what happens.
Right. Yes. Yeah. So good.
How does lambda L appear in the delta of S?
Delta of S lambda L does not appear. Lambda L purely appears from really this piece. The role of this delta is to, when you trade this, which is what Shiraj was saying, trading in terms of trading S in terms of the center of mass of it. So when you do that, you get this exponential factor out, but this exponential factor has been sitting in psi of p all along. So this is nothing but the Rindler boost. By exponential t, of course, I mean that's everything normalized so that your temperature is 1 or 1 over 2 pi, something like that.
But had the amplitude grown faster than S, had this local time delay grown faster than S, then you would have got faster than exponential.
Yes.
Because what you're doing is taking S and replacing it by the boosted S.
Right.
That boosted S you've explained to us is exponential in time.
Yes.
So whatever the local S is will
Absolutely.
be replaced by exponential in time. Right? And so any power.
Yeah, sorry. Local S is just the invariant.
Exactly. No, what I'm saying is that in flat space, if you do a calculation and you find the time delay, you get some function,
Right.
some function of S.
Right.
Then you're supposed to, if I understand you right, replace that function of S by function of e to the power lambda t.
Mhm.
Because that local S, proper S, is effectively e to the power lambda t.
Mhm.
And then if that local S was linear in S, you'll get exactly e to the power lambda t.
Right. Right.
If it was S to the power alpha, you would get e to the power
That is correct.
alpha lambda t.
That is correct. That is correct. That is precisely correct. Yeah.
All I was saying was that replacement is exactly taking the center.
Yeah. So the chaos bound is basically then saying that alpha cannot be larger than 1.
Yes. Exactly. Exactly. So this is in some sense, I think, consistent with these bounds that people put on phase shift, anyways. So it can grow at best with momentum raised to some power.
S square by t.
S square by t is
Should go farther than S square.
okay. Yeah.
Amplitude.
Yes. So yes, indeed, what you're saying is indeed true. Okay. So actually, I forgot what I was going to say. Okay. So right. So here you get. I mean, of course, at the end of the day, that this comes out to be saturating the bound, and the reason there are two ingredients. One is Sriraj is saying that the behavior of delta with respect to S and the component of the Rindler boost inside the bulk boundary propagator. Okay. So right. So you can ask this question that so a priori, do I know that maximal chaos is always, I mean, when is it guaranteed or when do I expect it? There are, of course, examples, various examples. One is, I mean, take a black hole, you're probably going to have this unless, I mean, well, in ADS-CFT, almost certainly guaranteed to have it. We know, of course, this SYK model, I say SYK model type Hamiltonian because by SYK model there are so many variants of those. But in the IR, essentially, you do always, almost always get the maximal chaos, which is basically governed by some effective Schwarzian theory. So the question you can ask just from this is that well, many, but some of them are, for example, so do I really need gravity? Absolutely necessarily, or some nonlinear theory would work in terms of this.
In a black hole background.
In a black hole background, yeah. Black hole is essential, yes. Or a Rindler horizon is essential.
SYK model is in counterexample to whether you need gravity, right? I didn't understand.
Oh, I meant in terms of a bulk calculation.
Oh.
Yeah.
But bulk by definition is a theory with gravity. What is your definition of bulk?
I mean, yes. Essentially, there has to be some notion of gravity, but
I think
may not be
probe calculation in a black hole background shows this.
something like that.
That answer is yes, right? Just
Yes.
from the red blue shift.
Yes. So it can be slightly more rich than that, but yes, essentially that's the answer. So right. So do I need gravity, or is there a nonlinear? I mean, some other nonlinear description? That's question one. And if yes, then do I really have an effective description of such systems? Something like the Schwarzian. Okay. So let me just very quickly do this. Well, just let me just mention this in terms of what I mentioned. This holographer's favorite semi-classical systems is Yang-Mills theory.
Introduction over at this point.
Introduction, I think, is long over.
I was doing
But I mean, just to keep you in the intro,
Yeah.
there's no other model known
Yeah.
besides the SYK without gravity, which is calculable and shows.
Yes, that is true.
No
That is
You're
true.
saying this or you're asking?
I'm asking. I'm asking.
I not that I know. Not that I know.
It's quite
I'm
strange.
sure we could in ON vector model and just the Wilson Fisher calculate to one some leading order one way. I'm sure if somebody really
I
put a
see.
gun to our heads, we could.
No, but it wouldn't saturate them.
No, to saturate.
That's what I
Yeah,
was-
yeah.
So probably one could, I don't know, with the resummation and all, but I mean, no model is known where it saturates, right?
No.
Besides SYK.
No. Yeah, that's pretty. Yeah, I mean, equivalently, you could say that if you have a Schwarzian theory, then whatever theory you start from, if you can make it flow to, or if it has a Schwarzian limit, then it will have a maximal chaos. Not other. I mean, otherwise we don't know. This is probably the most.
The distinction being that you don't want gravitons to take part in the scattering that's happening. Just the background and no.
Yeah. Okay.
But this whole f of s being replaced by f of e to the power t will always be true, right?
Yeah.
Now it's just a question of what f of s.
Yeah. That is absolutely right. Okay. So, well, still in the introduction, but okay. So what the standard picture is basically what you do is you start with some background, some SUN Yang-Mills theory, and you sprinkle in some other additional degrees of freedom. It's not important what this is, but basically, I mean, one standard story is you start with some, D3 branes, which gives you ADS5, etc., and then you can add other branes, which can give you some other degree of freedom, which are not the adjoints, but some quark-like objects and so on. So the whole point is, at least what I'm trying to describe is purely in that sector. We of course know that if I have super Yang-Mills n equals 4 super Yang-Mills at finite temperature, then in the strong coupling, because there's a black hole, maximal chaos is guaranteed. So it's nothing new. So what happens in the probe sector is the question, and there you can make things slightly interesting or slightly more interesting. Yeah.
Sector means you're not taking n D3 branes and back reacting them.
No, so by n, sorry, okay, so maybe let me go through slowly. So this n D3 branes are this by that I just mean the near horizon limit of that. So basically I just have ADS5 times S5 or some other compact manifold, and you can put a horizon also in there. So the probe sector means that when you add additional branes like this D7s and so on, they don't back react. That's all.
But
That's right. That's right. That's right. That's right. Okay. So the rough picture is something like this. Well, I mean, instead of doing it in ADS5, it's easier, or I mean, sometimes also more nicer in some sense to work in 3 dimensions. So let's take a BTZ background, for example. So the rough picture is something like this. So this, suppose this is the radial direction. So you have the boundary of your geometry, and I have introduced some cutoff here. So this is not not quite allowed to take this limit to all the way to infinity, and this cutoff you can relate physically to a physical parameter in the field theory, which is essentially the mass of the additional degrees of freedom that you are introducing. If you want, that mass is given in terms of some factors of temperature, alpha prime, and so on. It's not really important for us. So now the point is that well, there are various things you can do. The first step is to start with a string, for example. So if you have a string stretching from the horizon all the way to this UV, so that does have a classical profile which you can solve for, etc., etc. And of course, this one end of the string is at the horizon, which is at r equal to RH, and the other end is at some cutoff, which is RUV. And once you determine the classical profile of it, you can go into a semi-classical description by just calculating some small fluctuation. So this is another very simple semi-classical system that you can design, and then you can ask a similar question.
So the original string is going down into the horizon.
Going down into the horizon, yes.
So,
Yeah.
you know, so just to maybe predict what, so you're going to say that there's some chaos on the world, right? But then, you know, just like Sandeep mentioned, you know, you need the blue shift
Mhm.
to understand the exponential growth. So, are you going to say
Right.
that the world sheet will also
Have a
blue
horizon.
shift within? So, is there some kind of black hole geometry inside the world sheet?
Yes.
That's what you're saying.
Yes.
Some kind of horizon formation
Yes. Yes.
in the
In the world sheet.
two-dimensional black hole. Just I see.
Right.
With the induced metric.
In this case, in the induced metric, yes.
But and the BTZ is of course at finite temperature.
Yeah. I mean, in this case, it's almost kind of. I mean, okay, you can this classical profiles can be complicated enough, but in the simplest cases, it's almost obvious to see that this horizon will induce a horizon. That's completely straight. Yes, I did not draw it in that way. I mean, this is the straight thing that falls all the way to the. Yes, indeed, that's the easiest thing to do. But there are other profiles which you can actually solve for, etc. They're just a little more complicated to show that there is a horizon, but generically there is. That's the statement. Okay, so right. So let me very quickly say this because you have already guessed what's going to happen. So you start with the standard BTZ for example, in the Pfefferman-Graham patch, which looks like this, and then the simplest classical solution is just a flat or straight string all the way from infinity to the boundary, sorry, to the horizon. Of course, you have manifestly in the static gauge and so on. So this actually gives you an ADS2 worldsheet, which has a horizon in itself that is induced from the gravity. Now you take this and you start doing a semi-classical analysis, not quantizing the string at all. Just take the.
This ADS2 is the Poincare ADS2, right? Because and the space is R.
Yeah. So this ADS2 would be basically just, if you just forget about this term, it's up to this.
You just keep the dr and dt.
Yeah, you just keep the dr and dt. The simplest, this is really very simple. Just throw away the last term.
So I can't read whether it's Poincare or global.
Oh, it's not global.
It's Poincare.
Yeah. It's not global.
And this ADS2 right now with that stuff, there is no horizon, right? or there is.
No, there is a horizon here, right?
T is certainly going to 0.
So I started with the BTZ, which has a horizon.
Yeah.
And the statement is, I mean, it's almost obvious that if you focus on x equal to 0, this goes away, or x equal to, actually x equal to constant may also work. You have to just check whether this is a solution or not. I think it is, yeah, I mean, there is no reason why it should not be. Then you just throw away this term, and this is what you get, and it does have a horizon. Well, it's for a point or something like that, but okay. So right, so you have an ADS2 worldsheet with a horizon, if you like, in the Poincare, and then you can treat this system semi-classically. So consider fluctuations which have some linearized, which satisfy some linearized Nambu-Goto equation of motion, etc., which you can perturbatively solve, and so on and so forth. So what you can do with this is to calculate the 4-point OTOC. What you do is first solve the one way of doing it is, of course, you can solve the fluctuations, solve for the fluctuations, and then calculate the 4-point interaction term on shell, which will give you this amplitude. And once you, I mean, all of this will go through in with some irrelevant dressing here and there. And then at the end of the day, you get basically maximal chaos on the worldsheet event horizon, which is well, one way of saying that well, okay, here you don't quite have a theory of gravity. I mean, it's a theory of string. Of course, it's in a gravitational background, but nevertheless, it does have maximal chaos.
How and where are these insertions of operators if I want to think about? So there's a worldsheet, and then
Yeah.
what are the insertions?
So you can. So you mean in terms of the thermophile double kind of construction, it's the same at some particular time slices,
So
right?
insertions are actually in the background in the ADS3, PTC.
Well, I mean, it depends, right? I mean, because this x is a field viewed on the string worldsheet perspective, right?
Yeah.
This x, of course, this x is a coordinate in your background, but this is nothing but a scalar field. So you are introducing some scalar fields. So this is, you know, what we do in string theory. We quantize the string, but this is a very well, this is a very poor man's way of proceeding. You write down the classical system, and then you do a fluctuation. This is semi-classical first quantization on.
This worldsheet, and you're inserting sources on this worldsheet.
Right.
And then you're saying how it delta x.
Exactly. And that probably unsurprisingly gives you. So this is what I meant by worldsheet.
So you're saying that the scattering has the same S dependence as gravitational scattering.
That's right. Which may not be obvious.
It's not obvious.
This scattering is calculated how?
Nambu-Goto.
Nambu-Goto, yeah. So the fact that this has the same scattering as gravity is not at all. I don't know how to.
Is it from a contact interaction or tree level exchange?
In this case, it's a contact interaction.
Even a bit surprising because it looks like it's too derivative. So it looks like the amplitude would grow like S. I mean, maybe that's the point. I don't know, but that sounds like less than S squared. But okay.
Yeah, I mean, this I don't understand why it has the same.
Oh, one other question. If you did this calculation in flat space,
Yeah.
there's no black hole. You just
Yeah.
take a string worldsheet and you send some pulse.
Mm-hmm.
You might think that you would get some reflection back. But since we know that a left moving mode is an exact solution of the theory, the scattering there would be zero. Right? Is that right? If you did your same calculation in flat space, you would find zero.
Zero for what? The amplitude?
If you send something in and you ask
Yeah.
what is the amplitude for it to come back out. That's the
Oh.
net theory, right?
Yeah.
You would
That
get zero, I just
that
wanted to
should be
confirm.
zero. Yes, I think so.
So it's because this is non-trivial background.
Yeah. This is, yeah. In that sense, it's coupled to gravity or.
Yeah, I mean, even in flat space, it might seem at first like you get something non-zero. Because Nambu-Goto looks like it has interactions
Right.
at every order.
Right.
But we know from the Polyakov form that it just goes through.
Yeah.
Right?
I think that is. Yeah, I think that is right. It's the.
Would your calculation in the flat space case be the analog of sending in a left mover and right mover and getting them to collide, or would it be just two left movers? And then a state? I'm not fully sure. In the black hole background, it seems one thing coming out,
Mhm.
one like this, but
No way.
is Your scry minus has two halves. So is it that you have one?
Let me think. It.
I was thinking it was like this in some background.
In some background.
So you have.
The heavy operator was a closed string perturbation of the whole space time. Then on the world sheet it would just be this.
Whole space-time means the target space.
The ADS. Suppose you put a wave on that ADS on the world sheet. Of course, you don't even have. You have just.
I was just doing flat space. I thought if it's two light operators, you can do two things.
I
One-
like it. But actually, in flat space, even if you did what you did, the other thing we know in Polyakov is that they go through each other.
Yeah, but with even with it's not exactly a CF. I mean, he has some cubic. You have some cubic.
Some quartic interaction.
But quartic interaction comes from Nambu-Goto.
Yeah.
Nambu-Goto classically is exactly identical. It looks like a non-interacting theory, but it's basically identical, right? It can be rewritten as Polyakov, and then in the Polyakov case, left and right, they go through each other. And Nambu-Goto theory in flat space is a solvable theory
Yes,
because it's secretly free.
that is right.
Presumably the fact that this theory, that string motion in a black hole background is not integral, plays an important role. I'm asking.
No, I think that is right. I think that is right. Yeah, I think that is true.
I'm sorry, just
Yes.
to go back to the black hole question.
Yes.
I'm not getting this metric to be a black hole thing. Because,
Okay.
If you have a diagonal metric,
Yes.
is G upper RR equal to 0 is the thing for if you have some R equal to constant, if you claim that some R
Yes.
equal to constant
Yes.
thing is a horizon, in particular
Yeah.
it's a null surface, then is G upper RR equal to 0 is the diagnostic of a horizon, not G lower TT.
Let me.
Basically, you know,
No. So here all that we have done is take the BTZ in Poincare patch, write it in the Pfefferman-Graham form,
Yes.
so that your dr square, whatever you have. So you have something like this, right?
The Euclidean patch is not quite.
Dr square by f of r or something. So that maybe this is a different r. That you write as this.
Yeah, I agree.
So-
You take your final coordinate,
Yeah.
but if you just drop the dx square term,
Right.
the rest of the metric that you have, okay, is not a black hole metric. It doesn't have a horizon. For the horizon. In particular, that r equal to RH surface, okay, is not a null surface. That's easy to prove.
Okay, I can. do the following.
Well, I mean, yeah. Go ahead.
No, sorry, just to ask you the question in dumber way. If I rotate t to time to
Right.
Euclidean,
Yes.
it should be writable as dr square plus r square d theta square.
That's right.
If I set r equals rh, the first thing is fine, so I just get.
Yes.
The second one gives a single zero in r minus rh, no?
Right.
So then that doesn't quite look like r.
But that is what you do in standard. I mean, you absorb in your.
In the standard one, the denominator, this is towards Gautam's
It's the
point.
same. It's correct. Correct.
The
So if you-
denominator also goes to zero, no?
Mhm.
Like normally it's dr square 1 minus 2m over r.
Mhm.
So then because of that, you get an r square. You know what I mean?
Yeah. I
This is towards Gautam's.
Yeah.
one way, Saha way of saying it.
So suppose I instead of this patch, I worked with the Poincare patch where you have this form of the metric, which is
Use it R instead of R.
R equal to RH, it is null.
This is the same, suppose we use the same exercise that we wrote in the Schwarzian interpretive form.
yeah.
And then you drop the x part, then you clearly see that R equal to RH is
No,
not
but
even
it's a different metric.
It's not a.
there's just a coordinate.
No, I'm saying something very simple. Take r equal to constant as a candidate surface of a horizon. Then the normal one form is just dr. dr is the normal one form. Now, you
And you're saying that's not
claim
null.
that the normal has to be null. Then dr dot dr has to be equal to 0. So that's g upper rr. This is very simple.
So
So we are used to Schwarzian-like objects in which there is a another factor 1 over r minus blah blah. So then g upper r equal to 0 is the same as g dot tt equal to 0.
Yeah, so in these coordinates.
so in these coordinates,
This is fine.
this is fine,
This
right?
one is fine.
Yeah.
So
How Q index is.
okay, so can you ignore that then?
All right. This is fine. This
So
one is
in this coordinate, so let's take the discussion in this coordinate. And in this coordinate, x equal to 0 is a solution, which is fine. Now let's forget that. And this r, by the way, is not constant. This is the radial direction.
Here I agree with you.
So this is
If
the
you drop x here,
yes.
and if you drop x there, presumably it's not the same thing.
Uh,
No, so like go from here to there by just
But how is it possible?
You're not dropping x, you're dropping r. Then you're sitting at a fixed r.
sitting at a fixed r. Sorry, maybe
You're
we're
sitting at r equals rh, right? For the horizon.
oh, for the horizon, yes.
So it doesn't matter what coordinate and r gives. You know, these are. I think it's okay.
Wait. No, but I think he's looking at the induced metric along the string, in which
Yes.
It's not it's not the induced metric.
Let's first drop x. That's the induced metric along
Yes.
the string. Now you want to see whether this two-dimensional metric is has a horizon. So for that we want to see whether the surface r equals rh is a null surface. A null surface in one dimension is a surface in which the metric is 0. Let's check. R equals rh, first term is 0 because we're at r equals rh. Second.
No, Shiraz. This is the you see r equal to rh. Okay, I'm just going by how I would do it. So r equal to constant.
Yeah.
Let us say whether this is a null surface or not.
Yes.
So now the normal one form to this thing is dr.
Right.
Okay, now I do dr dot dr.
Yeah.
So that's g upper r.
Yeah.
G upper r is not 0.
It's very confusing because you're using this coordinates. But could I just go back and just look at the surface r equals rh?
Okay.
On that, the surface r equals rh, you don't keep the dr square term because r is rh. And the other term, dt square coefficient is 0. So the metric is null in that surface.
Yeah.
Okay, now the question about
The metric does not.
Metric is null meaning what?
on the submanifold, you've got a null metric.
Yeah.
There's a second question you correctly ask about whether the normal to that metric is dr. But in order to answer that question, you should work in a singular coordinate system.
Yes.
You should move to a Graham-Pfefferman, some sort of Graham-Pfefferman type question. I mean,
Eddington-Finkelstein.
Between these two is
No, it's just that, you know, what's the difference between this R and that R? Just the difference is that there is a normalization of the dr that is different. But that difference is an infinite normalization. Right, because his dr, the dr in this metric, and the dr in that metric differs by a factor that goes to infinity or 0. So, I'm saying this it's a very dangerous thing to do this when it is a singular coordinate.
So I'm a bit suspicious, I must
But-
admit, because locally it should be like after Euclideanizing it should be like flat space.
So
And it's not looking like
so to avoid that, could you pretend that this is
Yeah,
the
this one
coordinate
is
I'm
fine.
working
This
with?
one I'm fine.
And he just
So,
moved
okay.
to that coordinate.
Good.
Okay, I
From
can't
an
see
R-
the change, but okay.
So let's ignore.
Some function of r will make it dr square by r.
Yes.
It's true that that function blows up at r equals rh. That's
Yes.
the problem. That's what
Yes.
you guys are pointing at. He
Yes.
doesn't care about that.
Yes.
That function is blowing up. That compensates for double zero somehow.
That function is we can just forget about it. He's setting up this r is equal to rh and setting that r is equal to rh, which is the same geometrical manifold.
Yes.
Well, there's a little
Yes.
more to it than that.
But you'd be happy with this, right?
Why?
So
I mean,
let's.
in geometry.
No,
this
no,
is-
it's also how the particular surface is embedded in the underlying space. To claim that it's a really null surface,
Ah,
you know.
yeah. Could I ask, if we wanted to claim that it was, no, you're probably right. Okay.
also Sandeep got a conical singularity.
Yeah,
as
so
well.
in Euclidean space, this gives a
It's not
conical
it will
singularity.
become a singular.
See, it's not.
Again,
it's not
in the
flat.
RT coordinate system. So if you say that the RT coordinate system has
See, let me set R near RH, okay?
Yeah.
This is, dr squared
Yeah.
up to some constant,
Yeah.
plus R minus RH.
Yeah, okay, this can't
Which
be
is-
right because
So,
yeah,
so
this can't be. This can't be.
that's a conical, that's what I'm saying.
There can't be. This coordinate change
So
can't be right.
so
It has to blow up.
so forget about that. So
Yeah, I
so
agree.
sorry.
Yeah, can't be.
So sorry, forget about that. Yeah. But
okay,
this you are fine with, right? Okay, good. So let's go with this. Okay. Actually, forgot what I. Okay.
I'm sorry.
No. It's fine. So okay. So this is fine. And now yes. So there is that. Okay.
I think it's just a misprint in the dr square by r square.
Um,
Because it's the same coordinate r as appears there. Anyway, we like.
yeah. Okay. So all right. So let's proceed. So okay. So you can of course ask, is there a Schwarzian? The answer is actually almost obvious, but okay. Nevertheless, so there's a generic sort of set of steps you can go through to get that, which is simple enough. But I'll just mention this in words. So first of all, I mean it's ob
Actually,
yes.
sorry to
Yeah.
interrupt you, but I mean, it's a striking fact. Suppose I took in 4D a theory on a black hole background, but the scattering was just due to phi 4.
Mhm.
You would again get the chaos.
This I don't know.
No, it's not
Seems
clear.
very strange.
No,
It's
this
not
I
clear
don't
because the
know.
phase shift may be independent of energy.
Yeah,
5 to the 4 will give you independent of energy.
yeah.
And then it doesn't help that there's a boost.
So then what is
It's the fact that the number go to action is two derivatives. Every term in their action has two derivatives. So like gravity, its scattering amplitude grows with energy.
I see. So your x to the 4 interaction is two derivatives.
The whole action
Yeah.
is two derivatives.
The whole
Every
action
term
is.
in the action, like in gravity, is two derivatives.
Therefore,
Therefore, it will grow with energy. I could see that it would grow the same way. But
no, but I think that may be wrong.
yeah.
But yes, but what you are asking is I don't know the complete answer too. I mean, so if you have this boost factor, can you write down some nonlinear theory which will give you this maximal chaos? I don't know.
Your argument, any theory of Goldstone's would probably have the same feature or not.
Good point. I think yes. I think so. I mean, would have, I don't know if they maximize it, but it will grow exponentially.
Grow exponentially.
Yeah. It's interesting, right? The Goldstones have 4 derivatives. So it's almost something they grow fast. But maybe you don't have the exchange line. Maybe that's the point. But the 4 derivatives give you the same s square that gravity would with exchange.
There is no 4 derivatives.
You mean the interaction
You
term?
take nonlinear sigma.
I mean,
You have phi
Yeah.
square and del phi square.
Yeah,
Sorry,
yeah,
you're right. You're right.
it's always two derivatives.
But still, that's very interesting.
No, but if you have shift symmetry, suppose I take a theory with shift symmetry, then every occurrence of a phi has to be a del phi.
That is correct. So everything will have del mu phi, but then it can be a polynomial phi of phi.
So then it does have
multiplied
shift
to-
symmetry. Suppose I have a theory which has phi goes to phi plus c symmetry. Then phi should never appear.
In that way, but I was just saying, if you have a nonlinear sigma model, like
Oh, I'm sorry.
phi
You're
on
right.
S.
Absolutely. Yeah. Sorry. So quartic terms have to
be del phi over to the 4.
Del phi.
Let's take a theory which has a Goldstone symmetry because phi is shift.
I'm sorry.
Okay,
Yes.
that's a very simple goal. Yeah.
Yeah. Then it will be del phi to the 4. Then the whole thing will start with s square. And maybe the reason that this will be important is that this will be the same as. Okay, I don't know.
But then it seems like it's growing too fast.
Well, s square is also how gravity grows. Grows like s square by t. Now all this impact parameter
Okay.
stuff you have to
Okay.
do. Man.
Well, what do you want to do? We want to put this in a paragraph and just.
And it's important that this theory will have no cubic. So this will not have the exchange line. Because you can't make a cubic coupling with only derivatives. So the first term will be the contact term, which will have the same growth as a trivial exchange from Einstein's gravity,
Mhm.
which will saturate the chaos. I mean, in power. That's how it.
No, but maybe this is what Sandeep was saying. The nonlinear sigma model.
Yeah.
So once you go to the angular variables,
Yeah.
then it's like it's like sine square theta del mu phi
Yeah.
square. So it's not like there's any there's a
It's more complicated.
yes, no, there's a nonlinear symmetry of course being realized in terms of
That's like Wilson-Fisher theory, something like that.
I mean, there are always two derivatives,
Yeah.
but then you don't have every phi.
For example, one term is sine square theta del phi square.
Yeah. But that will be slower growth than the model I want, right? Model I want you can also make because there's a shift symmetry. In fact,
I'll tell you what I'm a little worried about. If you take a, we should go. If you take a model which is del theta squared plus del theta to the 4,
yeah.
or maybe you want del square theta.
No, del theta squared plus del theta. In fact, this is well known, right? The shift symmetry models, in fact, there's a causality coefficient.
That's
sign.
what I was
Yeah.
going to ask. I mean, then the del theta to the 4, if it's dominating, is it running into?
Is it running? I think that it's going the same powers graph because it's scaling like S squared. Since gravity doesn't cause trouble, this will not have caused trouble. And in fact, there's a bound from causality on the coefficient of this term.
This is Mimas.
Mimas term. And this will probably tell you that it's time delay rather than time.
Okay, well, that would be an interesting example.
I see. Maybe you have answered the question that I had actually, which is, yeah, I precisely had this question which I did not know the answer to. I mean,
Any other theory?
what nonlinear coupling that you need? It might be interesting to actually work it out, but okay. Good, good. So let me just very briefly mention these things. Right. So the generic, I mean, the answer is yes, there is Schwarzian. It's almost actually obvious how it has to be there. And the generic nature is the following: that Namo-Goto theory is, of course, it has a gauge symmetry, the standard worldsheet diffeomorphisms, etc. The embedding space has a conformal boundary, being ADS. And therefore, of course, you expect that there are large diffeomorphisms which are actually genuine symmetries of the system. So the statement or the claim is the following: that the soft modes which are associated to these symmetries are basically responsible for the maximal chaos. And the soft modes are again exactly as you expect, described by an effective Schwarzian. Which is this line of arguments, I think, is very similar to what people also do in Jacques-Title-Born gravity, to say that you do get Schwarzian action out of it, and you get maximal chaos and so on. So
You
it's
can also compute the S matrix.
yeah.
You've done that.
Well, no, not.
When you claimed that the growth was saturating,
Yes.
what calculation was it? I thought you computed an S matrix.
That's what I thought.
Well,
They're just calculating something.
Yeah. So that's what you mean, the amplitude you mean?
Yeah.
Yeah. Yes.
You computed the S matrix.
Yes. Yes.
How does it grow with S? Oh, there's no T because it's
Oh
one.
no, there is no T.
This is worldsheet S matrix. Right?
Yeah.
This is well, okay. So I want to be slightly careful here. So what you can calculate is basically, you know, the amplitude of these interactions, right?
And then you
So-
did something like make the pulses
Right.
in the black hole background and
Yes, exactly. That calculation you can do, certainly.
So listen, what is the initial state? What's the final state?
What's the initial state? What's the final state? So basically, what you do is you set up in terms of, you mean delta x's.
Yes.
So you set up basically I mean, it's the same. So in this case, the v and the w operators are the same. So it's just delta x, delta x, delta x, and delta x. Sorry, delta x at different times.
Okay.
Essentially that. So that calculation you can do, and from there you do see what.
then from here you convert it into a S matrix element, let's say.
In terms of this in state and out state.
Yes.
Yes.
And then you do it, right?
Then you do it. Yes. Yes.
Okay.
Yes.
All right. Wait, but the in-state, are they both coming? This question of left and right. Is something coming from inside the black hole or not?
I think so. Yes.
Yeah, the horizon.
Yeah.
And if you did this calculation, you compute it as a function of S.
Mm-hmm.
How does it go like a function? Just in flat. What I'm trying to understand is this analog of
So
something then boost.
it grows with S. I mean, you mean delta? How delta grows with
Yes.
S? Delta is linear in S.
Delta
That I think is true, yes.
So what does it mean that delta is linear? What grows linearly?
Just cross S matrix or element.
Yeah.
I thought what we were doing in
No,
the
no.
black hole background was you take a local S matrix, which was a flat space S matrix, and then replace S by e to the party. But I thought we agreed that the local S matrix here is true.
No, no. Okay, so let me see. No, maybe that's not correct. So you want to see the black hole horizon as a flat space, or
I thought what you were saying in the earlier case was you take this S matrix. Now it's very complicated in this full ADS space, but let's look at it as local, Einstein's
Right.
elevator.
right,
We get some local S matrix,
Right.
and then you replace that S by some function of t.
Right.
This I understand. Now, if you wanted to do the same thing here, the natural analog would be to do a local S matrix. The S matrix would be in flat space.
yes.
But I thought we agreed that was true.
No, but that is not 0.
Now this I'm getting worried about. Because isn't it true that in flat space, Nambu-Goto theory, left and right modes just pass through each other?
Despite the seeming fact.
Apparent interaction. This is how we quantize T.
Let me see.
Oh, I'm wrong about that. Maybe I'm wrong, but maybe the constraints are playing some role that I'm
Could
ignoring.
could be.
You just help me with that.
It's true that classically you can write Nambu-Goto as Polyakov.
Yeah.
That's certainly true.
That's
Yes.
certainly true. And in Polyakov action, if you set conformal gauge is definitely free. Conformal gauge
Right.
is missing the constraints. But, and so maybe you tell me the interaction comes somehow from the constraints. But just help me understand it from that. I mean, is there an interesting S matrix to calculate for flat space? So sounds a little doubtful.
No, this okay. No, I'm not exactly sure how the constraint will give you interaction, but that well, it's true that if you do this calculation, you don't get 0 at the near the black hole horizon. Now, what you are saying is, if I did the same calculation in completely flat space, I would get 0. Now, where is the difference?
Yeah, maybe you're getting one. You're seeing the difference between. Is your calculation seeing the difference between flat space and this black hole horizon in a crucial way?
It must be. Now, you want to see from the constraints.
No, if it's seeing the difference, then I have nothing to say. But I had thought the way the earlier calculation worked is that there was a leading order term that didn't see the difference with flat space. And there you just replace S by e to the power t. If that's how it's working, I don't understand it. If it's working some other way, we can go on. It's probably true.
This worksheet is fixed,
The-
right?
Yes.
In the black hole background.
Right.
Unlike, let's say, I'm not sure whether it's a similar type of thing where you would consider scattering in flat space, such that, like, for example, the Goldstone bosons and then translate that to the.
Well, let's look at a little bit of the world sheet
Yeah.
near the flat space. That's a world sheet in flat space.
Okay.
Yes.
Equivalence.
Yes.
And then the scattering there should be at very high energies. I would have imagined trivial. No, I'm probably wrong.
So what is the space for what is the piece of the worksheet that is approximately flat space?
Any little patch is approximately better. Just equivalence. Any little patch of a manifold is flat.
You know, there's a big separation between RS, I mean the radius and the string scale. Then of course what you were saying, but in the SOIP game there is a problem that the ABS radius of curvature turns out to be the same as the string scale.
I see. But here he's just doing a simple classical
Yeah.
calculation.
Yeah.
In that classical.
all that where what is the effective R radius here? The same as in the embedding.
The same as yes. That is same.
All I'm saying is the following. That if you do some very high energy scattering and you draw a little elevator around,
Yeah.
you can't tell that you were not in flat space.
I see. I see your point.
This would be true in the original calculation is what you showed.
Yes. And that originally, that's how the calculation is done. You say, well, I can't tell that I'm not in flat space, so I use a flat space amplitude. And then replace S by e to the power t. What's worrying me is that it seems to me that the analog of that s square by t is 0. Because
In 2 dimensions.
Well-
what I'm saying is wrong, I know, but just to help me, because it seems to me that in actual string theory, left and right moves go through each other.
So again, we face this intuition in terms of so delta of S is basically the change, is also written as the change in the on-shell action. The phase difference between in and outgoing modes in the diagonal approximation is just written is approximated by the change in the on-shell action. And here, if you take the left and right going modes, then the Nambu-Goto action, at least the quartic order, gives you a finite answer. So.
Yeah. So I'm fine. What I don't know what to say, but I would say do the same in flat space
And then it should go
and
to equilibrium.
show me that there's a big difference.
Okay.
I see.
Or if there's not a big difference,
Okay.
explain to me why.
Yeah.
Because it seems to me that
Yeah,
just
Yeah, I understand now. No, that, yeah, okay, that.
It goes through, so even in iconograph, nothing should happen.
nothing
Special
should happen, I
happen.
thought.
Yeah.
That's how we solve string theory. Right?
Yeah.
But maybe my intuition's wrong. You just
Even the fact that there is a horizon. If there
so
is
the horizon. See, this is what I'm saying. If the scattering happening in a local patch,
you should not see.
that's what I thought. I'm probably wrong, but just explain.
Yeah, this we can.
The out replicates exactly the Stanford-Shankar thing, but what you're saying is delta should be 0.
That's what I thought. I'm probably wrong.
I got it.
And do they calculate the coefficient? Do they say up to a constant?
No, I don't think it's an up to a constant result. But yes, I don't have an answer to your question, at least yet. But yes, I mean, it's something we can probably figure out exactly in what way it's different.
Are you like midway through your?
I'm probably slightly crossed midway, but I could rush if you wish. I mean,
You have to break for lunch and
okay. So in MS, about how much? 10 minutes. Okay. Okay. So no. That's very useful. Well, at least for me. So okay. So let me just quickly tell you what this is all about. Yeah. So this I already said that you can make the argument for a Schwarzian. So of course, if you want really to get a Schwarzian in an honest way, what you have to do is a purely two-dimensional worldsheet analysis, etc., which is well, may not be easiest thing to do if it's not hard. So what we do is take a standard or maybe even obvious bypass. We cheat. I cheat. I don't mean Rohan or Ovik is cheating, but so what you do is take the large, take the. No, what I mean is that this is not a reflection on their character. So what you do is take the large diffuse structure which is available for ADS3, and then you can do some projection. This project is under quotation because of a reason. Let me not get into that. But basically what you do is you take the Brown-Hainout diffeomorphisms, and then because you know how your worldsheet is embedded in the ADS3, you can construct some large diffuse on the worldsheet itself. And this function knows about of course the embedding. So if you do that, so there's what you can do is you can determine the Schwarzian as well as how it couples to the fluctuations on the string worldsheet. And one particular special case is you can impose that even the fluctuating worldsheet is an ADS2. So basically, not only the classical worldsheet is ADS2, whatever is fluctuating, if I see it as a change in the metric, that also preserves this ADS2. And there are solutions of that sort. It's not unphysical. So one particular usefulness of this constraint is you get the full nonlinear Schwarzian right on the money, because basically what happens is you have those two independent Schwarzians in your ADS3, and if you do the projection, at least the way this string is embedded, it directly just relates the two, and basically the on-shell action, the Nambu-Goto action, just gives you something like this, which is this is a function, arbitrary function. Tau is the standard worldsheet parameter now. It's an integral over one direction now, because it's now you can view this as a one-dimensional system. This alpha prime is the standard alpha prime of string theory, and epsilon IR is nothing but some factors of temperature and so on. So this is similar to what you get in a Schwarzian effective action essentially. So that's a very simple way to get that.
So this small f is a projection of the Brown-Hino,
Yeah.
but which one? I mean, it has a holomorphic and an anti-holomorphic.
Yeah, so it's you just equate the two. So that's what I call f. So f plus of x plus is equal to f minus of x minus, if you like.
Physically, you look at how the Brown-Hino diffeomorphisms look on the worldsheet, which is fluctuating.
Yeah.
And so you have to put in the coordinates of the fluctuation and ask what the Brown-Hino diffeomorphisms look. So coordinates will become put up.
So there's a constraint which relates f plus and f minus?
Yeah.
Yes.
Constraint being the worldsheet metric itself, because you're asking it at a particular point in x and here.
Maybe we can ask this.
Okay. 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 So that's that. That's actually quite easy. Well, I mean, as you can see, and you can do slightly. Well, you can do a lot more things with this. But one thing you can immediately do is try. I mean, this is the Schwarzian, that is fine. But of course, not all fluctuations on the string worldsheet is going to be are going to be the soft modes and so on. There are all sorts of things. So how do I know a generic coupling or a generic semi-classical degree of freedom couples with this Schwarzian sector? And to answer that, what you do is you relax your condition that the fluctuations are worldsheet preserving, the rigid worldsheet preserving, and then what you do is something simple. You say that because of this large diffuse, I can, given a set of fluctuations, I can map it to another set of fluctuations by doing this large diffuse, by doing essentially changing your metric, worldsheet metric in this way. So just take a Lie derivative along one of the large gauge transformations, and then you can expand in power series of either the temperature or alpha prime, or actually in this case both. So all that does is there are two things that it does. One is that it gives you a linearized form of the Schwarzian, which comes with a 3 derivative. So these epsilons are basically, if you like, the infinitesimal version of this f of tau. And you get a third derivative, so you expect that it's non-linearly corrected to the or completed to the Schwarzian. And not only that, you also get a coupling of these delta x modes with the epsilons directly. So once you have this coupling, it's actually almost if you do a little bit of analysis with the Schwarzian, purely Schwarzian theory, it becomes kind of almost obvious that any scattering between these modes, if you construct and extract out the Lyapunov exponent, is going to have the maximal chaos. That is simply because the maximal chaos is really governed by how epsilons, what their propagators are. Sorry? Epsilon e to the epsilon goes like e to the t.
Classical solution from this.
Yes.
From this Schwarzian.
Oh, yeah.
Because it's just epsilon, no other power or any
Right.
you get the exact
Right.
root.
That is right. That is right. Yeah. Yeah.
One more.
Yeah.
Shiraz, this is what isn't this the answer to your question?
Oh, sorry, I was spacing on.
Yeah. So here you are getting an effective action on the worldsheet now, right?
Mhm.
Projecting these coordinates. So projection essentially somehow taking into account the constraints, because once you do this, the action that you got was the Schwarzian instead of a free action,
That is right. Yes.
because it's nailed down somehow in VDS. I mean, it's clear, right? The action that you got after this was different. That's where the difference must lie.
Yeah. I mean, it's not a zero action. That's
Particularly
Because the action all lives at the boundary or something like that?
Indeed, yeah, that does happen.
Sorry.
so. Oh, I see. You are saying that it's not a flat
You can't
space.
think of it as a local.
So there's non-locality built into it.
fluctuation around something
I
which
see.
looks like ADS2 or the
Yeah, so this intuition of taking a local interaction and boosting your thing, that must be there.
I mean, it's fine, but not strictly.
No, I think it must be wrong because this if at least leading order local interaction booster will give you 0.
Well, I don't understand. These X's are propagating fields on the worldsheet. X's are not like gravitons. Gravitons don't exist, admittedly. But X does. X are propagating waves on the worldsheet. So why can't I think about local scattering of those?
yeah, that you
I
can
don't know why the X theory information all goes to the boundary.
at the linearized order it does. If you're solving linearized equations of motion, it does. But non-linearly it will not. As yes.
But X's are like matter fields on the worldsheet.
Yeah.
They propagate.
They don't.
So I just want to remind you of one thing. If we take ordinary string theory in flat space, even with the constraints, we can solve it in terms of 24 free Gaussian.
Yes.
This is just a fact. So I believe there's no.
Yeah, I mean we could go to light.
We can go to Light-Cone gauge, but in the end we've got a solution. The full solution of the classical theory is in terms of 24 free
Gaussian.
Gaussian.
The Light-Cone gauge formulation is unconstrained.
Yeah. Right. Right. Right.
So
Right.
it's free.
Yeah, that's right.
But this argument, if the local patch thing goes, it should not matter what is the worldsheet metric about which you're doing the fluctuation. Because anywhere local, I can always see it as what.
Because yours is ADS2, right?
Yeah.
Yeah.
But Shiraz's argument that you can take a
not
local
be
thing.
different about ADS2.
It should, but if it's very high energies, the scattering amplitude, you think doesn't care. So maybe you're going to the next order. I don't know. There's something different.
Yeah. Right. Okay. Yes. So, all right. So, okay. So let me. Well, okay. This is just a picture of saying the same thing, that there is coupling of the soft modes with the fluctuation modes, if you like, and basically these propagators are what eventually give you maximal chaos, because these propagators are nothing but the Schwarzian propagators of the Schwarzian theory. So. Right. Okay. So, well, I mean, there are many questions that you can, well, you have already asked, but probably more you can ask. So, one obvious thing is, well, it's a doable thing, perhaps also along the ones that Shiraz is suggesting. I mean, why bother only about the transverse fluctuations, what's going on with the longitudinal and so on, since if you are giving a semi-classical description of this, might as well give the full form of it. But then, of course, this is not a very honest to God two-dimensional analysis, not from the purely worldsheet perspective. It's having something and then projecting. But towards that, perhaps what you guys are doing might be relevant, or that might be the way to go. And of course, I mean. So the classical profile of the string that I was talking about is purely based on ADS, specifically ADS2, but it's not, of course, the general solution. There are many cases where it's not ADS2 and it's yet physically interesting. So what happens in those cases? Can I do a similar thing there, which I don't know the answer to. So okay, so in 10 minutes, or rather 10 minutes back it was 10 minutes, so it's okay. So let me just say a few things about each of the slides and not explain. So what you can do instead of answering, I mean, you can answer those questions, but there is a simpler thing to do, which is, I mean, you could mimic a similar calculation on a bunch of D branes, and we know that they are, I mean, there is a clear semi-classical description of that, and this is you can quantify that in terms of a scrambling time, how it scales with 't Hooft coupling and NC, etc. So which is what this slide contains. So all this is to say that there is a semi-classical regime, and you do have this notion of Lyapunov growth. Now let's take one particular case, which is very easy because it's analytically tractable. So what you do is you start with some ADS5 times S5 background and place a bunch of defect branes. such that the world volume theory becomes AdS4 times S2. So, let us take this theory with no event horizon anywhere in the background or otherwise. Now, what you do is you take this because there are gauge fields etc. on the brane, you can excite one of them, one of the U1 fluxes specifically in a form which basically has a constant electric field on the world volume. This turns on other modes of the flux also, other modes of the U1 field also, specifically something that knows about the current etc. So, the dynamics of this, the classical dynamics of this is completely governed by the Dirac-Born-Infeld action, which has information about the embedding function, this additional flux and of course, the radial coordinate etc., which you can solve for, and you can in particular you can take some simple embedding etc. So, what is the point? The point is now you can again do a semi-classical analysis, expand around the classical profile. Of course, on the brane you have basically three kinds of fluctuations: scalars, vectors, fermions etc., not etc., that is it. And then what happens is, if you determine their actions, what happens is that you scalar, vector and fermions, so their kinetic terms are contracted with a metric which takes this form. It is called the open string metric. This is not the metric that in which the background brane is put in, which is essentially AdS5 times S5. This is not AdS5, and it has information about both the metric as well as the flux. So, what is special about this configuration is that this open string metric which is here, it does have a horizon, and that horizon is basically given by this field square. By the way, I have completely absorbed, reabsorbed factors of alpha prime etc. So, they may not be visible, but should not be too worried. So, even though there is no fluctuation, even though there is no background event horizon, you do have the fluctuations seeing a horizon, and then you can try to calculate, try to see whether you can calculate this OTOC 4-point correlator by considering fluctuations of certain fields, and in this case the vector fluctuations do give you a complete analytic control. You can calculate everything that you want, and basically what happens is that at the end of the day exact same steps follow and you get maximal chaos on the brane horizon. So, even though there is no horizon in the gravity.
Independent of the value of the electric field?
No, it depends on the electric. So, that is at the temperature if you like. So, let me just show you the Lyapunov exponent. So, in case if you have temperature in the background as well as an electric field on the brane, the Lyapunov exponent that you get is something like this. It has temperature as well as the electric field. So, this is the black hole temperature, this is the electric field. So, if you set this to 0, it still has a factor, still non-zero. So, that is the, so roughly speaking this is the temperature that the brane degrees of freedom see. So, it is roughly
this is like the
that.
total energy density T4 e to the power 4.
Yes, yes.
And then you take the water group somehow.
Yeah.
So this seems like it's greater than the bound.
Well, I mean, yes, naively you would say that, but I don't think that's the right interpretation. You should say that what is the temperature? I think the brane degrees of freedom see precisely this temperature, not T to the, not T. It sees T to the 4 plus E square raised to 1/4.
That's your, this kind of thinking, where has it gone into in this theory?
Well, I mean, so if I for okay, so let me forget that there is a gravity at all. So just focus on the brane. So if I all I have is just the brane and its fluctuations, I can analyze those and I can see what sort of temperature they see, and they will always see this temperature. So I would not Yeah, that is true.
Then you can think of this as at some finite temperature. It's true it's got an electric field, but so what? Oh, is electric field inconsistent with finite temperature? Maybe electric field is inconsistent.
What electric field is? Why would it be inconsistent?
Because once you have an electric field, current keeps circulating.
Yeah.
It's not equivalent. What is this electric field?
Well, I mean, this is just a simple electric field that's on the brane. What it does is, after a while, it does pair create, starts this current, and so on.
Set up a current?
It does set up a current. But so in this limit, where so basically there is some work done on the system, and if you go away from the probe limit, of course, it will heat up the gravity background.
Yeah.
But in the probe limit, that is completely suppressed. So this is an artificial way of separating them.
So somehow maybe there's a way out. It's not quite equilibrium. Maybe you can't really set up.
Something like a steady state, if you wish.
I mean, in some strict sense, there's no equilibrium.
That is right.
This is a classical macroscopic electric field, not an electric field like in a radiation cavity.
No, it's a classical, yeah. It's a classical field. That is right. Yes, so in that sense, yeah. Right. So okay. So that's that. Well, I mean, you could ask about whether this has an effective IR description. That's I don't know. It might, but for that you really need to do. I mean, first of all, it has to have a certain soft sector existing and so on, which we don't know at least whether it does. And of course.
Potential, I don't think.
Yeah, maybe I should not keep you hungry for long. So last just in 2 lines or 2 minutes, I will absolutely finish. So this is a very you might say a very simple-minded approach, and I think it is, which is you can take a phenomenologist's point of view in all this, saying that okay, I don't really know what this is, where this Schwarzian and all this is coming from. All I know that in the IR I do have an SL2R global symmetry. So Schwarzian is certainly not the unique action. So I could start by writing down some, in quote unquote, IR effective theory, in which you just write down some functional which is a functional of a Schwarzian. So if I write down a theory like this, what is the chaotic property of such a theory? Of course, admittedly, this is likely to have lots of problems in Lorentzian signature, including ghosts and so on, but okay. So a simple family of choice or class of choice is you just take the Schwarzian raised to some power. So what you can do in this case, of course, you can again write down the classical solution, which is the same for all n. At least that saddle exists for all n, and then it's possible to carry out a But there is a similarity with some results, at least reported in the literature in terms of higher spin degrees of freedom. So there are claims that if you have higher spin degrees of freedom, some things like this can happen, and thereby certain higher spin theories are actually ruled out, and so on and so forth. So so that's just a curious observation that I'm reporting, and you might probably wonder about whether any higher spin sort of theory could give you a Schwarzian or Schwarzian power effective theory in the IR, even though it's problematic just by itself. So and the other point is that there are cases for which you do get maximal chaos, irrespective of the fact that you have some other integer. I mean, in particular, if you take n to be half integer, which is probably the next best thing to an integer, you still get the same maximal chaos, because this additional 0. And you could probably work out the string front of it in terms of this how much Schwarzian effective theory knows about quantum mechanics of the strings and so on. And of course, the general question is also that is there an effective description near any event horizon, and etc. So thank you for your attention.